So the third term is the Coulomb energy term. We know the positively charged protons present in the nucleus are always repelling each other due to Coulomb electrostatic force and trying to escape the nucleus, which will decrease the stability of the nucleus and reduce the total binding energy of the nucleus. So this Coulomb energy term contributes negatively to decrease the binding energy. Okay. So for a spherical nucleus of radius r, so why again spherical? Because we are deriving all this term based on the liquid drop model, and according to liquid drop model we consider the nucleus to be spherical in shape. And if there are z number of protons, then there will be z into z minus 1 divided by 2 pairs of protons, okay, which will be interacting that due to that electrostatic repulsive force. So it is like this. So suppose there are 3 protons, okay, there are 3 protons. So if you consider the first one, 1 2 3, if you consider the first one, it will act there will be interaction between 1 and 2, 1 and 3. With respect to 2, there will be interaction between 1 and 3, and with respect to 3, there will be interaction between interaction with 1 and 2. So you can say there are 1 2 3 4 5 6 pair of you can say 6 pair of 6 interaction, but you see these two are same. The interaction between 1 2 and 2 1 are same. Okay, again 1 3 and 3 1 are same, and between 2 3 and 3 2 are same. Okay, so in this way, so if you consider all these interaction, there will be only three interaction. Okay, 3 interaction. So similarly, if there are z number of protons, there will be total z into z minus 1, like this 6 number of neutrons, and but to ignore the mutual, the same term repeating again, we will have a factor of 2. Okay, so in a nucleus, if there are z number of protons, then there will be z into z minus 1 divided by 2 number of Coulomb electrostatic repulsive force acting. Okay, so if there are more number of repulsive force, okay, more pair of force, then what will happen? There will be less stability and the binding energy will be less. And this Coulomb, if you check, go back and check your electrostatic syllabus, okay, that you learned in semester 2, you will find that the Coulomb potential energy is inversely proportional to R. So generally the term was like this. Suppose we have 2 charges Q, then the Coulomb, the potential energy is like this, Q square by something 4 pi epsilon 0 or something like this. Okay, so this Coulomb electrostatic potential energy is proportional to 1 by R. Okay, so you can say like it was like something like U proportional to Q square by R, like this. Okay, so instead of Q square, here we are getting this Z into Z minus 1 divided by 2 term. So okay, Q is the charge, you know, 2 charges Q. So instead of Q square, we are getting this term, this many number of interactions, Z into Z minus 1 by 2, and in the denominator we have R. So what is R here? Here R is the radius of the nucleus, radius of the nucleus, which is capital R we will be using. Okay, so Coulomb potential energy is inversely proportional to R. So here you are taking the average value, not the distance between every proton pair is R, but on average we are taking this value. So the Coulomb energy term BC is proportional to Z into Z minus 1 divided by R. So we are not writing the factor of 2. So BC is proportional to Z into Z minus 1 divided by 1 by A cube. Why? Because again we know R is proportional to R0 to the power 1 by 3. Okay, so BC equals to minus AC Z into Z minus 1 divided by A to the power 1 by 3. So AC is called the Coulomb energy coefficient, which has a value of 0.711 mega electron volt. You may find that in different books, different values for the coefficients are used. You can use any number. Okay, and this negative term, the negative sign here indicates that the Coulomb energy term decreases stability of the nucleus or decreases the binding energy of the nucleus.